Let's start our seminar. It is my pleasure to announce the talk by Thomas Mertens from Ghent University. He will tell us about bulk observables in Jackiw-Teitelboim gravity. But before he will start, let me make some announcement that the next seminar will take place in 1 week, not in 2 weeks, just in 1 week. And next time, Samir Machour from Ohio will give us a talk about contrasting the fastball to wormhole paradigm. So now let's go to our talk, our today talk. Thomas, please, 1 hour.
Thank you. So let me first thank the organizers. Thank you for inviting me to give this seminar. So my talk will be about bulk observable in Jackiw-Teitelboim or JT gravity, and my talk will be based roughly on these 3 papers that have appeared in the last couple of years, and also some work in progress near the very end. So let me start by giving you a brief outline of my talk. So I'll first start by introducing JT gravity, and then describing it equivalently as a Schwarzenegger quantum mechanical theory on the holographic boundary. I will describe the Schwarzenegger path integral you can compute with that, and in particular, I will focus on the boundary 2-point function in this model. And I will use this as input to come to the main part of my talk, which will be a discussion about bulk correlation functions in this model. And in particular, I will discuss the bulk 2-point function. And as physical applications, I will discuss locality and an application to the information paradox. And then in the last part of my talk, I will talk about basically the Fourier transform of the previous part, which is the Unruh heat bath, the thermal heat bath surrounding a black hole. And I will discuss 2 probes of this. The first is a very operational thing. I will discuss an Unruh DeWitt linear detector. And then the second thing that I will do is I will discuss the bath spectral energy density. And I will end with a conclusion and an outlook on what remains to be done. Okay, so let me first give you an introduction to Jackiw-Teitelboim or JT gravity. So JT gravity is a specific version of a 2D dilaton gravity model. So I've written down the action here, and it was introduced by Jackiw and Teitelboim in the 80s. So it consists of the Ricci scalar that I've written here, the cosmological constant -2, because I will be interested in an asymptotically ADS spacetime. I want to study holography with this model. And then this gets directly coupled to the dilaton field phi, as I've written here. So this is a very simple gravitational model that you can study, and it's a very interesting one, as I will show you. And if we define this model on a manifold that has a boundary, we need to include a Gibbons-Hawking-like boundary term, where k is the extrinsic curvature trace and gamma is the pullback metric to this boundary curve. Now, there are several reasons to study this specific model of dilaton gravity, so I mentioned a few here. The first is that you can view this as a dimensional reduction in the S-wave sector of 3D pure gravity. A second reason is that this model appears quite universally as the near horizon theory of near extremal higher dimensional black holes. A third reason, and this is how it appeared in the literature in the last 5 years, but by Kitaev mainly, is that it describes the low energy sector of all known SYK-like models. And then, as a toy model of gravity, it's very interesting because it's solvable to a very large extent. It's solvable, including coupling to bulk matter fields, at least in part. And it also leads to an understanding of the role of higher genus and non-perturbative contributions to the gravitational path integral. Now, for my talk here, or for the purposes of my talk, I will be interested in looking at bulk quantum gravity physics you can distill from this model. So let's now imagine we insert this action in a path integral calculation. Then the very first thing we are going to do is we're going to path integrate over the dilaton field phi, because it only appears as a Lagrange multiplier in the action. This immediately fixes r equals -2. So the Ricci scalar is fixed off shell. And in 2 dimensions, this is sufficient to conclude that the geometry is fixed as some patch of the ADS2 manifold. So I've written here the Poincaré patch, ds squared equals minus df squared plus dz squared over z squared, where z is the radial coordinate, where z equals 0 would be the holographic boundary, and z goes all the way to infinity. And I denoted the Poincaré time coordinate by big F, a notation that will become clear further on. So big F and big Z are the Poincaré time and radial coordinates. Now, because the geometry is in any case some patch of ADS2, it is convenient to briefly discuss the major patches or the major classical frames that we will encounter during this talk. So let's first transfer to light cone coordinates. So big U and big V are light cone coordinates in the Poincaré coordinate. So U is time plus radial coordinate and V is time minus radial coordinate. And then I can rewrite the Poincaré patch in this form, as is of course well known. And you find this geometry or this patch of the ADS2 manifold directly in the near horizon regime of an extremal higher dimensional black hole. Now there's a second patch or a second frame that will be of interest during this talk, which is the black hole frame. And I can get to this by performing a chiral coordinate transformation starting in the Poincaré patch, where I define new light cone coordinates small u and small v. And the relation between big U and small u and big V and small v is just by a hyperbolic tangent function, where beta is a parameter in this transformation. Plugging that in, you find this metric, and you directly find this metric when you're studying the near horizon regime of a near extremal black hole in higher dimensions, for which the temperature, which will be 1 over beta, of course, this parameter that I introduced here, will be proportional to the square root of the mass of this higher dimensional black hole. So these are two important patches to keep in mind. And on this slide, I just draw the Penrose diagram for these two patches. So on the right is the holographic boundary. The smaller green triangle is the black hole patch, and this is embedded within the bigger triangle, which is the Poincaré patch. There's also the global frame for the ADS2 manifold, and this is just a strip. This is this entire wide strip that is here, but I won't be needing that during this talk. Okay, so now let's get back to our problem. So we path integrated out the dilaton field phi, fixing the Ricci scalars to be a negative constant. Now, at the level of the path integral, this means that only the boundary term survives in the action now. So that was this Gibbons-Hawking-like extrinsic curvature trace term. So now we need to impose boundary conditions to find an interesting model. And I will consider, or to define these boundary conditions, I will consider my boundary to be a wiggly curve that I parameterize by f of tau and z of tau, where tau is some proper time coordinate along this curve. And again, f and z are the Poincaré time and radial coordinates. And I will consider this curve as a UV cutoff, which carves out a shape from the ADS2 geometry. Now, to specify this curve, I will specify I need to specify boundary conditions. And these are the conditions that I will choose. First of all, I will choose this curve to follow the asymptotic Poincaré geometry. And if you, basically look at the metric and plug this parameterization in there, you'll find that the z coordinate of the curve and the f coordinate are related in this specific way, where epsilon is a UV cutoff. So z equals epsilon f dot, and the entire curve is parameterized by just one function f of tau. As a second boundary condition, I will choose my boundary curve to follow a value of constant large value of the dilaton field. And this is the constant large value that I'm choosing here. So epsilon is going to 0. Epsilon was my UV cutoff. And A is a dimensionful parameter that will define my specific theory or my specific model. With these conditions, you can just evaluate this Gibbons-Hawking boundary term immediately. You just, compute the pullback metric close to the asymptotic boundary, which is just 1 over epsilon. And you compute the extrinsic curvature for a curve that for which the z and f coordinate are related in this way, and you find this expansion 1 plus epsilon squared, and then this expression, which is a Schwarzenegger derivative of this undetermined field f of tau that was left here, and then higher order terms in the epsilon expansion as epsilon is going to 0. And if you plug that in, after doing a holographic renormalization step, you find that the dynamics here is governed by this action where the Lagrangian itself is a Schwarzenegger derivative of f with respect to tau. So to be complete, I've written down the explicit expression for the Schwarzenegger derivative here. And there's a prefactor here, a coupling constant that I call big C. And big C, is proportional to 1 over the 2d Newton's constant because, I started with that prefactor, but it's also proportional to A, where A was a specific value that I chose here. And you can see that the dynamics of this model is fully given by a single degree of freedom, f of tau, which is a time reparameterization of Poincaré time f as a function of some proper time coordinate tau. And you should compare this derivation actually to the Chern-Simons-Wessel-Witten topological duality, because in that case, the large gauge transformations of Chern-Simons become the dynamical degrees of freedom of the WCW model. And the same thing happens here. the large gauge transformations, in this case, they would be the large coordinate transformations that do not leave the boundary invariant. These are precisely these time reparameterizations that we have here. They become the physical degrees of freedom that live at the boundary. This analogy is no coincidence because you can literally embed this derivation within that framework. When you write JT gravity in a gauge theoretic way as an SL2R BF gauge theory, you can see that it's actually identically the same kinds of dualities that are at play here. Another comment is that, so we have this coupling constant big C here. You can see that we are probing the semi-classical regime when big C is going to infinity, because that is where the Newton's constant is going to 0, or well, in the path integral where h bar is going to 0. I should also mention that big C here has the dimensions of length. Its dimensions fully come from this A parameter that we have here. And this, well, this shows that we expect quantum effects of this model to be important in the IR, not in the UV, and we will see that explicitly later on. Okay, so what we have seen from this calculation is that JT gravity reduces to an integral over the boundary frames f of tau. Now, for the purpose of going into the bulk, which of course is the goal of my talk, we will require the expressions for boundary correlators in JT gravity, and in particular in the thermal theory. So here I've written down a path integral expression of the kinds of objects we need to know before we are able to compute bulk observables. So I've inserted some operators, and I will specify in the next slide what they will be. So they're labeled by some index H1, H2, and so on. And we insert these in the path integral, and I path integrate over this Schwarzenegger field, over this time reparameterization field, f of tau, where the action is this Schwarzenegger action. It is convenient at this point to reparameterize a big F as in terms of a small f, so the variable Poincaré time as a function of tau. I now rewrite it as a tangent of pi over beta times f of small f of tau. And this is the Euclidean version of the black hole frame. The relation between the Poincaré frame and the black hole frame was a hyperbolic tangent in Lorentzian signature. Here we're in Euclidean because that's where we're going to do all our calculations. So this is just a tangent. And now this is a reparameterization of the black hole time coordinates, small f, instead of the Poincaré time coordinates. And this small f is actually a reparameterization of the thermal circle because I'm doing the thermal theory. Euclideanly, this means we have a periodic thermal direction. And this f of tau is giving you a reparameterization of this thermal circle. So here's a sketch of the thermal circle, and then this asymptotic curve, this wiggly boundary curve, that is being reparameterized by f of tau. There are also some technical details that I have not shown you here. I haven't mentioned, or I didn't mention what this precise integration manifold is or the measure, but you can look at the literature if you want to know that. I don't need these. All right, well, I'm not going to present the details here for the purpose of this talk. So the question we still have to answer are, what are the natural operators to consider here? What are the operators that we want to be looking at? So in order to get some inspiration, we will take a massive scalar field in the ADS2 bulk and look at its asymptotic expansion. Now, because the geometry is always fixed to some patch of ADS2, we can just solve the Klein-Gordon equation in ADS2, even off shell in this case. So what we're doing here, just solve box phi plus m squared phi equals 0 in ADS2. Asymptotically, this is the leading behavior as you approach the holographic boundary, where big Z and big F, again, are the Poincaré radial and time coordinates. Now, at the boundary, big Z was equal to epsilon times F prime. This was the wiggly boundary curve relation that we imposed, basically. And now it is convenient to rewrite everything in terms of a new radial variable that is just epsilon. So I lump all of these other factors together into a new, what I call the new boundary value of my field. So there was a tilde here. Now the tilde is gone because I've combined everything by definition into this object here. Now the generating functional in ADS-CFT for boundary correlators, well, you can just do it in this case. It's just a 2D application of the generic story. And well, at the first line, you have the well-known expression for that. So you can see the CFT 2-point function appearing here if I take two functional derivatives with respect to these phi tilde fields. So this is in Poincaré coordinates. Now I plug in the previous expansion to rewrite everything not in the Poincaré coordinates, but in terms of these proper time coordinates. So just plugging that in, you find this expression. And now you can see this operator that appears here. And this operator is a very natural operator to consider as an operator insertion in this Schwarzenegger theory. It is a reparameterized CFT two-point function that you then insert in the Schwarzenegger path integral. And so you integrate over all possible f's in that integral. This operator is called a bilocal operator because it depends, of course, on two times, tau1 and tau2. And it's labeled by a number h, which is the conformal weight of the dual operator. So here I've written it explicitly, and here I've written it in terms of this small f, which, well, you can just plug it in to see this relation. Well, I should also mention that there is also another way of looking at this operator, another origin of this operator. You can view it as a boundary anchored Wilson line when you describe JT gravity in its first order formulation as an SL2RBF theory. And that boundary anchored Wilson line obviously also has two endpoints, so it's automatically a bilocal operator. And you can show that you can actually get to this precise operator. Okay, now, well, several approaches to go to this, or to obtain correlators in JT gravity that have such insertions have been developed, and they exist. So here I just give you an overview of the different methods that have been developed throughout the years. So, well, I won't go into any of these methods, only to mention that there are several methods and the results of these methods all agree. So we're quite confident that we know the answer of the Schwarzenegger path integral with these operator insertions. And I'll just give you the answer now. So I'm not going to give you the derivation. You can take a look at the literature if you want. I'm just going to give you the final answer. And I'm going to only show it to you for the two-point function. So that means one bilocal operator insertion in the Schwarzenegger theory. So one of these O operators here. There is an interesting, well, graphical depiction of this. So I've drawn the disk here. So this is the gravitational disk. The red line is a holographic boundary. I've drawn two black dots here, which are the 2 points of the bilocal operator, and I've connected them with this blue line here. And the expression for this amplitude, so a single bilocal operator in the Schwarzenegger theory, which is a reparameterized boundary 2-point function, is given by this explicit expression. So this expression has two integrals, two energy integrals, 1 over E1, 1 over E2. It has two of these Hamiltonian propagation factors, or Boltzmann factors if you want. Tau here is the difference between the two times of the bilocal operator, and beta is the inverse temperature. Then there are densities of states here, rho 0 of E1 and rho 0 of E2, which are the Schwarzenegger, well, the famous Schwarzenegger density of states. So these are these sinh 2 pi square root E formulas. And then there is this last factor. So in the numerator, we have this gamma function. So by the plus minus symbols, I mean that you have to take the product of all cases. So there's a product of 4 gamma functions here in the numerator. And this is the piece that actually couples the E1 and the E2 integral to one another. So this is the explicit expression for a single boundary, for a single Schwarzenegger bilocal operator, or the boundary 2-point function in JT gravity. I haven't given you the proof or the derivation of this, but I am going to use this or exploit this to go into the bulk in a couple of slides.
Excuse me, Thomas.
Yes.
Can you ask during the talk?
Sorry?
Can I ask the question?
Yeah, sure.
What do you mean Schwarzschild?
This theory, the theory with the Schwarzenegger action. So this one. So this is a concrete path integral problem. We have a path integral over this f, and we can insert some operators in here, and our action is a Schwarzenegger derivative action. And the interesting operators.
Schwarzschild, not Schwarzschild.
Yeah, Schwarzenegger. I haven't used the word Schwarzschild throughout. I've only said Schwarzenegger, I hope.
I see. Thank you.
Okay, so this was the expression for the Euclidean boundary 2-point function, or one single Schwarzenegger bilocal. Now, for the purpose of the talk further on, I will be needing the Lorentzian version of this, so we will have to Wick rotate these things. Now, well, okay, if I go back to this, you can easily see that this thing has a divergence when tau, the time difference, is going to 0 or when it's going to beta, simply because in those two cases you lose this exponential suppression in the energy integrals. But if you draw this, or if you draw this for complex time, these two divergences are actually part of branch cuts. So what I've drawn here on the vertical axis, this green line is the thing we just computed. These are the Euclidean thermal 2-point functions. So this is tau equals 0, this point, the origin here, and this is tau equals beta, where there are two divergences. But if you draw the real-time axis, then you can see, well, just by looking at the expression, that you get a branch cut here all the way along the real axis, and a similar one here. So then if you want to go to real time, you have two options. You can come from the top and just go right above this branch cut, or you can come from the bottom and then go right below this branch cut. So there are two real time 2-point functions that you can construct. And here I've written down the expressions. So they're exactly the same as the previous ones, except that instead of a tau here, I have IT and I have a plus or minus sign choice, and this corresponds to these two options. These two 2-point functions would just be the two orderings of the two operators. So just the two Whiteman 2-point functions you can write down. Now, it is also interesting at this point to mention what this expression actually looks like qualitatively as a function of t. So now I am in Lorentzian signature, and t is the Lorentzian time separation between my two operators. And I can study this thing, this expression as a function of t. And what you find is that this function of t is always decaying, and it starts with the early time pole 1 over t to the 2h. This is actually the classical pole. This is the thing you would have if you would not do the path integral over the Schwarzenegger degree of freedom. So this is the early time behavior, and then at very late times it gets very strong quantum gravity, or Schwarzenegger in this case, fluctuations, and its late time decay is power law. It goes as 1 over t cubed, instead of what you actually expect in a CFT, which is, well, for an ordinary thermal CFT 2-point function, at late times you expect an exponential decay due to quasi-normal modes, but you see that this gets changed in this model because that is where gravity, or Schwarzenegger theory, or JT gravity, is strongly coupled. So this is indeed, as we predicted qualitatively, just by looking at the dimensions of the Schwarzenegger coupling constant big C in the beginning, that the quantum gravitational interactions would be important in the IR. And this is what you can literally see if you look at the behavior of this 2-point function as a function of time.
Thomas, hi.
Yes.
I have a question. So quasi-normal modes like are responsible for the decay over scales of the order of beta, right? So in this setup, like when the quasi-normal modes are responsible for the late-time decay, right? But like their decay rates are of the order of inverse of beta, right?
Yes. E to the minus 2 pi over beta times t, or something like that.
Yeah, exactly. So my question is, like, when you transit between these two behaviors that you observe here, do you have like an intermediate exponential decay?
But oh, you mean can you see the exponential decay before you see this power law
exactly
decay?
Yeah,
you can do that, but you need to tune your parameters in a clever way. But yeah, you can do that. You can first see the exponential and then see the power law.
So it's there. Yeah, you're just saying that like you have to be careful what you mean by the time.
It's just that at very late times, and this is very late with respect to that big C that I introduced, the Schwarzenegger coupling. So it's T much bigger than C. It will always be power law, and the power law will always win over the exponential decay.
Yeah, sure, of course. Okay, very good, thanks.
Okay, one final comment here is that, and I will need this later on. So I have two energy integrals. So this is a canonical correlator, but it's very easy to get the microcanonical answer because you can just strip off the Laplace E2 integral. The Laplace transform is literally written here. So to go to the microcanonical ensemble is very simple in these formulas. Okay, so that was all of the introduction that I need in this talk, because my goal is to compute bulk observables, not boundary observables, but we will exploit these boundary correlators to do that. So that was, of course, the entire goal of this lengthy discussion we had up to this point. Now, in quantum gravity, defining a bulk observable, and by that I mean a diff invariant operator, requires care. For instance, for a scalar field phi of x, So you would write this when you study quantum fields in curved space-time. But in full quantum gravity, you need to specify what X is. You need to specify the bulk location in a geometrically invariant way. And because we're doing holography, preferably we want to do this in a boundary intrinsic way. So now we will just make a choice on how to define our bulk points, and we will compute things from there. So the choice we will make, or the definition we will use, is some sort of radar definition of a bulk point. So given 2 points, or given 2 times on our boundary proper times, small u and small v, we define a bulk point, big U and big V. So big U and big V are the Poincare light cone coordinates from the boundary reparameterization big F. So this is the off-shell reparameterization big F. So we're doing this inside the Schwarzenegger path integral using the radar definition of a bulk point, where big U, the coordinate we want, is just equal to F of small u, and big V is equal to F of small v. So small u and small v I give to you beforehand, and then you can construct big U and big V using this mapping. And physically what you are doing, so I've drawn a picture here. So I've drawn a blue clock here. So the ticks are the ticking patterns of these clocks, and a different red clock here. And at a specific proper time along these clocks, I send in a light signal, and at the second time I will extract the light signal, and where these two intersect in the bulk, this will define my bulk point. And you can see that if the clock differs, so if F differs, the red one versus the blue one, you will actually construct a different physical point. So this means that the observables we have defined, and now I have fully defined them in terms of times on my boundary clock. So I've anchored my observable, or the location of my observable, fully at the holographic boundary. But now they become implicit functions of F, of the reparameterization of the gravitational variable. So any observable that I construct is a function of F of U and F of V. So it's at a point big U and big V, but they are in turn given by F of U and F of V. So what this means is that there is a contribution in the correlator from the implicit dependence on the geometry, big F, through this construction. And this is visible, for instance, in computations, or in commutator computations in particular, which was done by Donnelly and Giddings. They did it perturbatively in higher dimensions and not using this particular definition. But they showed indeed that this implicit dependence that you have here, when you want to define a diff invariant operator, that this is really important. So this is, yes.
What do you mean bulk gravity? You have quantum gravity, in principle, summation of all genus and so on, or semi-classical approximation to the bulk?
I'm not doing any approximation at this point. I am using the fact that for all off-shell geometries, I always have some patch of ADS2. So the geometries are not as wild as you would generically expect in any theory of quantum gravity. JT gravity has a very restricted set of geometries. They're always ADS2. The only physical information is this boundary clock, basically. And I've drawn 2 different off-shell clocks, and I've constructed a bulk point. I've drawn the bulk point with these different clocks.
But for bulk quantum gravity, we have to make a sum overall genus.
Oh yeah, I will come to the sum over genus further on. I am assuming only the disk topology and the Euclidean calculations contributes here. The disk topology is captured by the Schwarzenegger theory. When you go to higher, or when you want to include higher topologies, you have to, include other things as well. You're absolutely right. I am assuming only genus 0 here. For the Euclidean calculation that I will be doing, of course, because this is just a Lorentzian picture that I'm drawing. Okay, so my observables have an implicit dependence now on the gravitational variables. That's what you get when you try to define an observable or a diff invariant operator. Now, to supply these operators, I will, just as before, couple JT gravity to a bulk matter action, and I will take the massless scalar for simplicity. So my total theory is the JT theory that we had in the beginning, plus a massless scalar field that we have here. Now, the matter 2-point function in a fixed frame big F, just the CFT 2-point function, this massless scalar 2-point function, so phi 1, phi 2 in the CFT is just given by the log of the distance between the 2 points. Now, the expression that I've written here looks a bit more complicated. It has this denominator here, but that is just because of the boundary conditions. We have the holographic boundary where I am imposing Dirichlet boundary conditions for my matter field. So this denominator here is just the image charge. But this is basically just a CFT 2-point function of a massless scalar field that I've written here. But notice that it depends on big F here. It depends on the Schwarzenegger or on the time reparameterization field that I want to choose. So this is an off-shell operator that I'm going to insert now in the Schwarzenegger path integral, in the gravitational path integral. So after doing this, now I insert this operator in the Schwarzenegger path integral. So this entire procedure that I'm describing here is a two-step process. First, we integrate over matter to get an operator, a gravitational operator that we are then going to insert in the Schwarzenegger path integral and do the integral over the reparameterization field, or as I explained in the beginning, the integral over quantum gravity. So that's the idea of the calculations that I'm trying to describe here. Now, we want to insert this operator in the Schwarzenegger path integral, and this looks more complicated than the operators that we know how to calculate, these bilocal operators. But there is a simple trick. You can just write this operator as a double integral of this bilocal operator that we had at the very beginning. And well, of course, what you're going to do is you take the Schwarzenegger, the expectation value in the Schwarzenegger theory of this operator, and then you're going to integrate twice the answer you get. Now, this trick that I'm describing here, this actually coincides with the HKLL or bulk reconstruction prescription to map bulk operators into boundary observables. So in the HKLL prescription, any bulk operator is written as an integral over a kernel times boundary operators. If you do that calculation for ADS2, for a massless scalar field, you would find that that kernel is just a Heaviside function. And this is just basically truncating those integrals that we have here. So this is literally the HKLL prescription applied twice to the two operators in this 2-point function. But now this is done for any off-shell f of t. So we do this within the gravitational path integral. Okay, so well, what we need to do now is very simple. We just compute, or we take the answer for the boundary 2-point function or a single bilocal operator insertion in the Schwarzenegger theory and just do those two integrals. And what you find is this expression. So it looks very similar to the one we had for the boundary 2-point function. There's only these sine functions that appeared here just from doing these integrals. So it's a very simple expression if you know the previous one. And what does it look like? So what I've drawn here is a plot. So the plot is Euclidean. So I've put one point somewhere here, which is this dashed line here. And then I've drawn several profiles at fixed Euclidean time separation, so the blue, green, orange, and red one. And then I've drawn them as a function of the radial coordinate of this second point. And you can see that these functions are quite smooth. You can see a hint of a singularity or well, a divergence developing as the 2 points are going to coincide, obviously. But that is all that happens. So these functions are quite well behaved. There's no funny things happening as you change t, z, and z prime with respect to one another. So the only thing that happens, as I just showed you here, is that you get singularities when the points coincide in Euclidean, which corresponds when they are light-like separated in Lorentzian. Then you get singularities, and the singularities are log divergences. And this is actually what you would expect because the operator we started with already has this logarithm in it. So when 2 points coincide, you already see, of course, that you're going to get a log divergence. So this is all as expected. Now let's try to get to some applications for this, or let's apply this to understand some of the physics. The first is about bulk locality. So I have defined these operators to be diff invariant. I have not imposed them to be local operators. So bulk locality is either true or not, but we just have to show it. We have to prove it if it's there or not. Now, if they're local operators, of course, they should commute by definition for space-like separation. So this commutator would have to be 0. Since the commutator is just the difference of the two orderings for the bulk 2-point function, and I have mentioned that you can get both orderings for the, well, at least for the boundary 2-point functions, I mentioned this. Obviously, this extends to the bulk 2-point function. So we have all of the ingredients to check this, and this is indeed satisfied. This commutator is 0 for space-like separations. So the operators we have defined are mutually local operators in the full bulk quantum gravity theory. Now, I would like to refer also to this paper from Malacena and collaborators for another construction, a different construction of diff invariant operators that also turn out to be local. So what we seem to conclude from this is that JT gravity, when you insert matter operators in there, is more local than you would generically expect in quantum gravity. You generically expect non-localities to appear simply because of this gravitation. Okay.
Сука!
It's okay?
Sorry, I think it was just some
Yeah.
inappropriate guy. I'm very sorry for this. He expelled.
Okay, no problem.
I have a question. The fact that there's more locality, I wonder if it's because the metric commutes with itself in JT gravity, unlike generic quantum gravity. The canonical conjugate of the metric is the dilettante pi. So
yeah. I imagine this was just because the metric is not as wild as you would generically expect in quantum gravity. So,
but not as wild would mean that quantum effects are smaller. You're saying that there's no obstruction to defining local operators. I'm not explaining anything, but since you're making an exact statement, it should have an exact explanation. And I thought the exact statement might be that the metric commutes with itself.
Yes. Okay. Thanks. Okay. So, well, JT gravity is more local than we generically expect in quantum gravity. That seems to be the conclusion from this calculation. Now let's go to a second application of this, which is, well, the breakdown of effective field theory. Because the near horizon region is like an IR region in these calculations. It's very similar to the late time regime for the boundary 2-point functions. And that means that you have strong quantum gravitational effects there, and in particular deviations from the semi-classical Rindler correlators you would have very close to the horizon. And this would seem to have implications for the information paradox, because if you insist on defining bulk operators in a diff invariant way, this can lead to the near horizon region being very different from the semi-classical story. There's strong quantum gravity effects close to the horizon simply because we're anchoring our observables very far away to the holographic boundary. And this would cause a breakdown of effective field theory. To get some further intuition into this, so, well, I won't do the calculation here, but just as we defined bulk points operationally, you can define pairs of bulk points operationally, and then compute the geodesic distance between these pairs of bulk points. And infinitesimally, of course, you just construct the metric again. So you can give an operational definition of the infinitesimal distance squared, or of the metric, like this, and you find that the prefactor is just, again, this bilocal operator. And you indeed get strong deviations close to the horizon in this geometry from this. Now, of course, I should add some reservations to these conclusions. This is for this specific model, even though, as I mentioned at the very beginning, JT gravity is quite universal for many, well, for higher dimensional black holes and so on. And it's also for these specific bulk operators, for operators that you construct in this very specific way using this radar definition. Less natural bulk operators might exist that do not have this property that I mentioned here. So these are some caveats to take into consideration here. Okay, so now I'll move on to the next part of my talk, which is about basically the Fourier transform of the previous calculations. And we want to look at the Unruh heat bath and how these quantum gravity effects modify that. So I want to look at the spectral content of the bulk 2-point function, which would probe the black hole thermal atmosphere, or the Unruh heat bath. And I will discuss two quantities for that. The first is very operational again, it's a detector measurement. And the second one would be the bath spectral energy density. So let's first start with the first one, the detector measurement. So we will define an entire world line trajectory of an Unruh de Witt detector operationally, just like we have done before, by just using the same radar definition that we have been using, but now instead of just defining a single bulk point, we define an entire time-like trajectory of our detector here. So I've drawn, again, two boundary clocks here, and I've constructed a bulk point using both of these clocks. And now I choose a fixed value of z, the z that's written here. And for t from minus infinity to plus infinity, then I construct an entire trajectory of a clock here. So this is just the same radar construction, but now of an entire trajectory of an Unruh de Witt detector. And along this world line, we will introduce an interaction Hamiltonian that I've written down here, where mu of t is a detector quantum mechanical system, and it couples linearly to the bulk quantum field phi. So this linear interaction Hamiltonian was studied in, well, the late 70s and the 80s by Unruh and de Wit. And this is the definition of the Unruh de Wit detector. And now I want to look at, just like they did in the 80s, I want to look at the transition probability for our detectors to go from its ground state, 0 det, to an excited state with excitation energy omega, without any information on the excitation of the quantum field theory matter state, which starts out in the Poincare vacuum. So this transition probability, you can just write it in first order time-dependent perturbation theory like this. So there's this interaction Hamiltonian. The initial state is the vacuum for both the detector and for the matter fields. And then the final state is some excited state, and then all of the quantum field theory states that are compatible with this. And I sum over these mod squared to get the probability. Of course, well, as you always do, it's more convenient to go to the transition rate. So you just divide this by big T as you take T to go to infinity. And you can simplify that expression basically by removing that sum over all QFT states that's in the middle here. And you can write this as a product. The first piece is a purely detector piece. So it lives only in the quantum mechanical Hilbert space of the detector. And then you have a piece that is fully in the matter sector or in the CFT sector that we will study. And it's a bulk matter 2-point function along the world line of that detector. And then you need to take a Fourier transform of that thing. So this is just a standard calculation people did a long time ago. Of course, we will not be interested in this detector matrix element here because this is just specifics about the detector. We don't care about that. We want to know about the quantum fields. So we will drop this detector piece in the following. And now our strategy is obvious, I think. So we have a bulk matter 2-point function here. So we will view this again as a gravitational operator and insert this in the Schwarzenegger path integral. And what we basically are doing here is just Fourier transforming our bulk 2-point function that we have studied in the past few slides. That's basically what we are doing. Now for simplicity, I'm going to give you the answer in the microcanonical ensemble instead of the canonical one. They're very simply related, of course, they're just a Laplace transform in front, but the expression looks a little bit more tractable if I do it in the microcanonical ensemble. And this is the answer for this response rate. So this has an interesting interpretation, this answer. So, okay, these first pieces, this 2 times sine z omega over omega squared, this is not very interesting. This is just an interference factor coming from the image charges across the ADS2 boundary. So this is something you always have. It's not interesting. It's not probing black hole physics. It's probing boundary conditions at the holographic boundary. But the second piece here, that's the interesting one. That is the matter emission probability. So the probability that our black hole is emitting an excitation of energy omega. But you can see that there is this Heaviside function that has appeared here. And this Heaviside function signals back reaction effects. So it means that no energy omega greater than the original black hole mass, big M, can be emitted to the detector probe. This is something you would not see in the semi-classical Unruh heat bath. And indeed, we can take the semi-classical limits to show that these expressions are generalizations of that they include quantum gravitational effects. By taking the limit where M is very large, so we have a large black hole and our excitation is very small, has very small energy compared to this mass. And then we can just literally approximate these formulas and you find this formula. So in particular, this piece is just the Bose-Einstein or the Planckian black body spectrum. So in the semi-classical limit where you turn off quantum effects of gravity or the Schwarzenegger quantum effects, you see that you indeed just find the Bose-Einstein black body spectrum. This is just the standard Unruh type of calculation, but now we have a generalization of that. We have done the path integral over the Schwarzenegger degrees of freedom exactly here. Okay, so what we are going to do next, so everything up to now, well, as was asked before, has been about the genus 0 topology or the disk. So now we're going to try to include higher topological effects. And including higher topology in gravity is important. Typically, you would expect that they would be strongly suppressed by this kind of factor. You would get this factor if you insert the Einstein-Hilbert action next to the JT action that I've been studying here. And you can see that if that number is 0, which has an interpretation as an extremal entropy of the higher dimensional black hole, if that number is large, then you can see that higher genus effects would be strongly suppressed in the calculation. But we have learned in the last couple of years that they can be important in parametric regimes where this suppression is compensated by another enhancement, such as late times or small energy separation. And I list here two, well, famous recent examples of the last couple of years. So the replica wormholes to find the page curve is one example where this kind of, well, parametric regime is reached. And also the ramp regime that governs the late time average correlation functions of the boundary theory also requires these kinds of effects to appear. Now, it is important that when you try to do these calculations where you include higher genus effects, that the higher genus expansion is asymptotic. So this requires a non-perturbative completion. And for JT gravity, a double-scaled random matrix integral was shown by these authors to complete the genus expansion, or to at least be a possibility to complete the genus expansion. And this was studied in particular in this in one of these papers for multi-boundary amplitudes. And we have studied this for boundary correlators. And then in a paper after that, Phil Saad has studied this much more extensively. And his calculations show that when you want to study higher genus effects for boundary correlation functions, that the contributions of higher genus effects, that they only correct the n density factor you would have in the correlator. What I mean by that is, for instance, for the 2-point function, which is the only one we will be doing, if you remember, we had a double integral over energy. So you had a rho 0 E1, rho 0 E2. You just replace these by the pair density correlator in the matrix ensemble that is supposed to describe JT gravity. That's the only thing you should be doing here to incorporate all of these higher genus effects. Now, what is this pair density correlator? So in the simplest case for the Gaussian unitary ensemble, you can look at textbooks and you find that there's a nice expression for it, at least in the regime where the matrices are large, which looks like this. And this has an interpretation, these three terms, as a disconnected piece. This is the sign kernel, and this is a contact term. Now, some important features of this pair density correlator in this ensemble is that it has level repulsion. So if the two energies come close together, there's a quadratic zero or quadratic level repulsion, as you can see here. And it also has high frequency wiggles with a spacing that is very small. It goes as e to the minus s0, and we are going to assume that s0 is very large. These wiggles are just coming because there's an e to the s0 hidden here in this row within this sign function. Now, the important point of this is that this result is actually universal for all Hermitian random matrix systems, at least in some suitable kinematic regime. You cannot be too close to the spectral edge, and your energies cannot be too far away. Then this answer, this GUE answer, is actually expected to be correct also for JT gravity. You just need to plug in the correct row of E, which is, well, at leading order, it's this one, into this expression, and you find the pair density correlator with all of these assumptions in there, of course. Now, geometrically, this equation has a nice interpretation. So what I've drawn here is, again, the disk with a single bilocal line. And then I've started adding higher topological corrections to that. And they fall into distinct classes. So this diagram, it has a disconnected higher topology on each side of the line. And these diagrams here, where the topology on the left and on the right doesn't talk to each other, this gives you the disconnected piece of the pair density correlator. But in the last class of diagrams, you have higher topology that goes across the line. And this gives you a connected piece to the pair density correlator, or the sign kernel of the last slide. Now, this was all for the boundary correlators, and we are interested in bulk correlators. So now we make a proposal, and that is that since our bulk correlator was written through that HKLL reconstruction formula and the radar construction fully in terms of a boundary correlator, we propose to just insert the higher genus effects directly in the boundary correlator, which we know how to do. This is what I just sketched before, and then just do that double integral and find a proposal for the bulk correlator that includes higher genus effects. Now, this is a proposal, and we have, well, the result we will obtain makes sense physically, or it has a nice physical interpretation, but we cannot prove it at this point. At least in the regime that we will be interested in, which will be small energy separations, we believe this proposal well, has the physics we expect, but we have no proof. Okay, so this is again a caveat at this point. This is how we will, or what we will define that higher topological corrections mean for bulk correlators. Now, if we do that, or if we assume this proposal, then we immediately obtain this formula. So it's very easy then to see what needs to happen. This detector response rate just gets, well, there was a cinch here before, but now it's the pair density correlator m minus omega divided by rho of m. You can see that if you're in the regime where you turn off higher topology, then the pair density correlator is again dominated by the product of the single densities. So then the rho of m cancels the numerator and denominator, and you just have rho of m minus omega, which is just a cinch. So you can see that this is a generalization of that well, includes these random matrix kind of effects. So here I've written the formula again. I've rearranged the formula a little bit. And if you plot it, you get something like that. So the red curve here is the one you would get if you do not include these random matrix effects. And if you include them, you get these wiggles here, and then you get the quadratic zero as omega goes to zero. So that's the main effect of these random matrix effects. They all appear at very, very small omega, at ultra low frequencies. That's where this level repulsion thing is happening. And that is where you get these corrections to the results, to the Schwarzenegger results that I mentioned previously. Now, this formula has a very suggestive interpretation as a product of probabilities. So this piece here, this rho m minus, so this pair density correlator divided by the single densities, you can view that as the probability of the black hole system, the underlying black hole system, actually containing two levels spaced by omega. And if omega is too small, and well, the black hole system is supposed to be chaotic, then it shouldn't have two levels that are very closely spaced, precisely because of this quadratic level repulsion. So this factor is taking that into account. Does the black hole indeed have levels that are separated by this, this energy omega? And then the second piece, that's roughly the same one that we had before. So this is the probability of matter emission from such a system. And of course, we have this interference factor that is not interesting. So from this, we view this Unruh heat bath as a direct probe of the chaotic level statistics of the black hole. And this is, all of this was defined in a very operational way. We insisted on anchoring everything to the boundary. And this is something that a detector would really measure, of course, given our assumptions on how we treated higher topological corrections to the bulk correlator. And this has a nice physical interpretation. Now, I was going to talk a bit about the heat bath itself, but maybe due to time reasons, I should just show you the pictures. So I'm going to skip the calculations here. They're quite analogous as the ones I showed you for the detector. I'm just going to show you the pictures for the Unruh heat bath energy density. So let me go down a bit. So, okay, so I'm just going to show you this picture here. What I show here is, well, the energy density, omega n omega, and n omega is just the number operator, a dagger a. So this is the energy density as a function of omega. And then the red result is just the Planckian black body spectrum in 1+1D. And then the blue result is the one you would get if you include the Schwarzenegger corrections. So this is, you can see that there's a higher occupation in the heat bath, in the Unruh heat bath. This is again only the disk, this plot. So this does not include higher genus effects. So you can see that there's a slightly higher population of the Unruh heat bath, and there's an explicit check you can do. So I mentioned it here, and it's true in this case. So this result is consistent. That's what I want to say. There's also a generalization you can do of this Unruh heat bath calculation to other kinds of matter fields. And I did the calculation also for a fermionic field. So everything up to this point was for a matter, for a massless scalar field. You can do it for a fermionic field. And here I've plotted the result again. So the red one is just the semi-classical Fermi-Dirac spectrum. And then the blue one is the one that includes Schwarzenegger corrections. So the JT gravity on the disk, quantum gravity corrections. And you can see that, yes. Yes.
Can we say that the Planckian formula for radiation is deformed in such a way that temperature disappears?
The temperature disappeared?
No, you say is there a correction to the Planck formula, if I understand?
Yes. It's a correction to the population statistics of the energy levels of the heat bath.
So it doesn't have the original Planck formula.
No, it's different than the Planck formula. It reduces to it if we turn off quantum gravity again. So that was the check I did.
Yes, it's how it looks like your new deformed formula.
So I haven't shown you the analytic expression here. It looks very similar to the ones I showed you for the detector response rates.
So strictly speaking, there is no notion temperature now.
Sorry, there is no?
There is no temperature because temperature is like.
But there is a temperature. Everything is just computed as a canonical ensemble calculation from the boundary perspective. It's just that the population statistics is not exactly the Planckian black body law anymore.
Okay. Thank you.
But it will be it if you again go to the semi-classical regime. So this is supposed to describe a correction to it if you do the Schwarzenegger path integral instead of just evaluating it on the saddle.
Temperature still related with the black hole mass?
Well, that is an on-shell relation again. So either I do the calculation in the canonical ensemble or in the microcanonical, and I just specify the boundary temperature or the total energy that we have, and that's it. The relation between the two is only valid in the semi-classical relation, semi-classical regime. Does that answer your question?
Yes, thank you.
I see there's a raised hand. I don't know if...
Hi, can I ask a simple question?
Yes, sure.
When considering contributions from higher genus, do you need to add contributions from non-orientable surfaces?
No, I'm just taking the ordinary JT gravity, so the fully orientable one. The bosonic yes.
I see it.
Okay, yeah, you might general or try to do these types of calculations in other JT gravities, so either supergravity or non-orientable and so on, and you go to different matrix ensembles. I will mention something about supergravity in the end, but yeah, I'm assuming just bosonic orientable here.
I see. Thank you very much.
Okay, so right. So this was the result for the fermions, which is quite similar. And then, well, so these two plots, they were just for the, again, genus 0, only the disk contributions. But you can again go beyond the disk. And I'm going to draw a plot here again that is, again, in the microcanonical ensemble. So this is, well, the answer at very, very low frequency. So you can see that omega is very, very small here. And this green and red line, those would be the occupation or the energy occupation if you do not include higher genus effects. And again, you can see these wiggles and then the quadratic level repulsion here at ultra low frequency. So this is where the random matrix effects or the higher genus effects really dominate at super low omegas. Okay, so finally, let me mention a couple of extensions that we're trying to understand, but haven't fully understood them yet. So the first is well, just to generalize this to a charged black hole. So we learned that for the uncharged case, the boundary theory is just a Schwarzenegger action. If you do it for charged systems, there's also an additional U1 free boson action, and the action was written down a couple of years ago in this paper. So it looks roughly like that. So the first one is the Schwarzenegger action we have been studying throughout this talk. And then this lambda of t is a new degree of freedom, is this U1 free boson, and it couples to the Schwarzenegger potentially through some chemical potential, as is written here. And then you can think about introducing charged matter fields into the bulk and trying to make them observable. So to make them gravitationally observable, we've already done that, but now they would have to be observable also in the electromagnetic sector. So that means that you would have to dress them by electromagnetic Wilson line as well. And the resulting operators you get, you can again link them to boundary operators in this combined model, and the bilocal correlators in this boundary model have already been determined. So in principle, we have all of the ingredients we need to try to understand the bulk physics, again, with our definition of bulk observables that we have been using for charged black holes, and see whether quantum gravity changes anything to our quantum field theory and curved space-time understanding of these. And then another extension is to go to supergravity. And the story there, at least the initial parts of the story, are all the same. So by this, I mean n equals 1 supergravity. N equals 1 supergravity has a boundary description in terms of an n equals 1 super Schwarzen. And instead of parameterizations of a circle, this is primary parameterizations of a super circle. So, well, just to be a little bit explicit, I've written the reparameterization functions here, but they're not important for what I want to say. And again, you can try to give an operational definition of a bulk point, in this case in superspace. And you can do exactly the same definition. Given two boundary times, and in this case, they're times on the super clock, let's say, tau theta and tau prime theta prime, you can again use this radar construction to fix a point in the bulk and to define the location for a matter field, in this case, a super field there. And this allows you again to write your bulk correlation functions fully in terms of the boundary by local correlation functions, these n equals 1 super Schwarzen correlators. And one of the things you find, which is as expected, is that this differs from the bosonic JT model only in the quantum corrections. And this, of course, makes sense since the classical solution doesn't have fermions turned on. So you will only see the difference between this supergravity calculation and the bosonic calculation once you go to the quantum gravitational effects, once you couple to the gravitino, basically. So, well, this leads to some version of super Unruh effect, you might say. Okay, so let me end with some conclusions and an outlook. So first, well, all of the calculations that I mentioned were done in a very specific model, in the JT gravity model, but we expect some of these physical lessons to be universal. So let me emphasize the two main physical lessons that I think I discussed. So the first one is that strong quantum gravity effects in the near horizon Rindler region are possible when you use, or when you insist on using these diff invariant observables. And the second one is that the Unruh heat bath can probe the underlying black hole chaotic spectrum at ultra low emission energies. So what is on the to-do list? So I already mentioned the supersymmetric and charged cases. They would be tests for the universality of these constructions. And well, we would be interested to see whether these same physical conclusions hold in that case, or seem to hold in that case. A more ambitious goal would be to propose a definition, not of, well, a different definition of observables, because the observables we have defined here, they give you some quantum gravity generalization of the fiducial observers you define in the Unruh heat bath. So the static observers, the observers that don't fall into the black hole. Now, it would be interesting to propose a definition of infalling observables and try to see whether we can do anything with the Schwarzen path integral with these. Maybe we can, well, it would be ideal, of course, if we can just do the integral exactly, but maybe we can do it in perturbation theory to find some interesting physical lessons when we define infalling operators, but in a different way. And then finally, another possibly, well, it seems a very ambitious goal, is to try to embed this entire construction in an evaporating setup. So everything here was for the non-evaporating black hole. Now, semi-classically, when you have an evaporating black hole, you can realize that by imposing absorbing boundary conditions at your holographic boundary. And what this leads to is an equation of motion where E of t, so E of t is the total energy in your bulk space-time. And now dE dt, so the change of total energy in your space-time, is proportional to minus the energy. That is the equation of motion you get if you impose absorbing boundary conditions, or if you allow energy to leak from your system to sort of mimic evaporation. But this equation is the one that is actually replacing the Schwarzen equation of motion, so the saddle of these gravitational path integrals. So we would look for a path integral or a Lagrangian first, for which the equations of motion look like this, in order to try to describe the full quantum effects of something for which the saddle looks like that. Now, this is a dissipative equation of motion, so you would need to write down a non-local action for that. So well, that is again an open problem that I would be interested in thinking about. Okay, so thank you. That was everything I had to say.
Okay. Thank you very much for your very interesting talk. Questions, please. We'll have some questions. Igor Ivanovich, are you want to ask a question, please?
Yes. Thank you for a very nice talk. You studied quantum gravity, including black holes. Now my first question is, what is quantum black hole?
What is quantum black hole?
Yes.
Are you looking?
English, I guess. In this model, at least.
Well, okay.
You consider black holes in
Yes,
a classical sense, I understand.
but
Right now, we
not,
could ask question, what is quantum black hole?
yes. So the calculations that I'm doing are all just thermal ensemble calculations, and at the saddle of those calculations, you would find a semi-classical geometry that has an interpretation as a black hole. So in this sense, this is incorporating all of those effects you would get from what you would call quantum black hole. But I'm not sure what you're asking precisely. I'm not going to write down a metric or something for the.
Okay. Then let me ask another question. Consider your 2-point correlations for field phi. When one field is inside black hole, it has a field outside of black hole. Is there something specific for this case?
That would be very.
Outside.
That would be very interesting to study, but this radar definition that I use does not allow one to go inside the horizon. It's only for exterior measurements. So yeah, that would be very interesting. I agree with that.
I see. Yeah. I have one more question. I'm sorry. In quantum gravity, usually we say that at Planck's length, we should find something new. Yeah. Do you have some evidence that there exists something like Planck's scale in GT model?
But you mean a very small scale, right?
Yes.
Very small. So this model, it's modifying the IR, not the UV. So that is special about this 2D model. The quantum gravity is really happening only at very late very late times and very long distances. It doesn't do anything with the UV. So one might say that this model, this model is not a microscopic model of gravity. It doesn't correct or it doesn't cure divergences if 2 points coincide. So for instance, you could see that in the formulas that we still had the CFT pole for the boundary 2-point function. If the boundary 2-point function, if the 2 points were to coincide, that thing would still diverge. And if this was truly a microscopic theory of quantum gravity, for instance, this shouldn't happen. So this model is different than the higher dimensional versions in that respect.
Okay, thank you very much.
Okay, the next question from Ruka. Ruka, please.
Hello, hi, nice.
Hi.
Thanks for the talk. So I have just 2 questions. The first is related to the modified rate, the Unruh detector rate that you showed, the one corrected by quantum gravity. Can you show again the formula, if possible?
This one, or the one with the matrix effects, or without?
Yeah, the one in the case of Unruh de Witt.
But this is the final one.
Yeah, so basically you said that basically you recover in the semi-classical approximation like very large black hole.
Okay, so yeah, this is the previous version of the formula. Yes, here.
Yeah, this one. So I just want to understand physically what happens. So basically, of course, you have this Unruh de Witt detector, and you are saying that if you're in the full quantum gravity regime, you will have some correction to the formula, the usual, the standard Planck distribution. Yes. So what happens? Like the rate decrease or increase due to this quantum gravity correction?
Yeah, that depends strongly on which ensemble you're studying. So it's not in the canonical ensemble. So not for this, but for the bath spectral density, it just went up, right?
Mm-hmm.
Sorry, I should show you the picture. This one, the blue one is higher than the red one. So the population is higher for all levels, basically. That's the effect in the canonical ensemble. If you study it in the microcanonical ensemble, it's not well, you cannot make a statement that, oh, this is higher than what it used to be. Some pieces are higher, some pieces are lower.
So it's not very clear physically what is going on, let's say, in terms of
it's not very clear to make a statement like, for instance, it's always higher or something like that. You need to make a more refined statement. Sorry, I can show you the form. Yeah.
Okay. So my second question, so as an outsider, I would like to ask, okay, you are studying 2-dimensional black hole in JT gravity.
Yeah.
So does this study help or may be useful in some way to really understand some aspects of 4-dimensional astrophysical black holes?
Well, I mentioned at the very beginning that if you go to the near horizon regime of near
extremal black hole, right? That's
near extremal, right? So JT gravity is describing the first deviation from extremality.
But more than that, there is no, let's say, more like close relation to some.
Well, JT gravity is not universal for any possible black hole. It needs to be near extremal, unless, for instance, for the 3D BTC black hole, then it can just describe the S-wave sectors, not necessarily near the horizon, but everywhere. Yeah,
okay.
But it does have some universality to it. There is a large class of black holes for which, in some regime of the black holes, the physics contained in JT gravity is actually describing the essential features, or at least we expect and hope that that is true. And there have been many papers written by now that try to look at the relevance of JT gravity for higher dimensional black hole physics. So, yeah.
Okay, just a third quick question. So of course you are assuming that there is also a cosmological constant. So what happens to the kind of two-dimensional action if you don't put a cosmological constant? Can you also study something interesting?
Yeah,
like,
so
the poles and so on.
I was of course interested in negative cosmological constant because I want to do holography, but there also exist versions that have positive or zero cosmological constant, and they have also been studied. Not as much as this one, though. I mean, this one has been studied most, but yeah, there is literature on the others two options.
Okay, thank you.
I would say this one is best understood.
So I mean, I think maybe does this idea is I mean, the holography that you use anyway helps also in computation, I think, right? As compared
to because my definition of a bulk observable, I used or I anchor things at the holographic boundary, and if you if you're in the sitter or something, then it becomes you cannot do that. And
okay, thanks.
Okay, the next question from Shravan Kumar, please.
Hi, Thomas. Actually, part of my question is asked by Luca, the last question. So, but anyway, I have another question about, I mean, you concentrated on ADS, so you computed correlation functions in ADS, but which, if you do time rotation, you can get the correlation functions in de Sitter, right?
Well, you have to watch out with that, right? I mean, to some extent, yes, but
why some extent? I mean, well, I don't know about black holes much. At least in cosmology, inflationary correlations are related to correlations in ADS. That's what Marlesina paper is about. So he comments on that at the end of.
But you can do some things in the sitter version of this, and people have studied this. So there are a couple of papers about that. But yeah. But I think you probably have to be careful in, for instance, saying that, oh, I just put an eye somewhere and that's it. Yeah.
Okay. I don't see more questions.
I think in the chat there was a question from Michele.
Okay, please.
Michele, you can speak.
If you want to see some slides,
see this 23 and 24.
What is your question, please?
Michele Nardelli, are you there?
Are you here?
Well, he's here, but.
She cannot unmute herself.
Maybe I can ask some question in between.
Maybe she cannot ask question. Maybe there are some problems. Yes.
So if you don't mind, let me ask some questions.
Alexei, please ask your question.
So first, Thomas, thanks for the nice talk.
Thanks.
And maybe I missed something trivial, so maybe my question is really basic. But you're talking about black holes in 2 dimensions and then about holography. Maybe I missed the point. What is a holographic dual to all of that?
Well, I haven't, so this is not a microscopic model of holography. I'm just describing a gravity model that is in ADS, so it has a boundary, and then I'm describing things in terms of that boundary. So all of the dynamics can be mapped to this degree of freedom that is living at the boundary.
Yeah,
I'm not describing
what this be? It's like it's what, quantum mechanics?
Yes, the Schwarzenegger theory, that is effectively describing this thing. It is very much the same as the Chern-Simons WCW description. So in the analogy, I'm describing everything in terms of the boundary WCW variables.
No, I understood that you are not describing in terms of boundaries. This I got, but I'm just curious, what could be the boundary model then? What lives on this boundary?
The Schwarzenegger in this case. But again, this is not a microscopic model. This is just an effective model.
I see. Okay.
Okay. The next question from Igor Mo, please.
Hi, at least in 2 and 3 dimensions, Einstein-Hilbert action will give you a topological field theory. You do not have propagating degrees of freedom. Is this the case for JT gravities then?
There are no propagating degrees of freedom in the bulk. That is definitely true. But there is a degree of freedom living at the boundary. So there is local, well, there is something more than topology to this model. That's what I want to say. And that is described by this reparameterization at the boundary. But there are no gravitons in the bulk somewhere. There's only a boundary graviton. This situation is very analogous to the 3D gravity case, where you also only have boundary gravitons.
I see. All right, thank you. And just a speculation, going to 3 dimensions, there are many people working with super translations, let's say the BMS group in 3 dimensions. Do you know if there are any work trying to connect these 2 programs, like the BTZ black hole in 3 dimensions and how super rotations act on those black holes?
You're asking about how that 3-dimensional story would be in 2D with the super translations and so on, or?
Yes, if you.
Yeah, I don't know. I haven't studied that, but well, this entire BMS stuff is of course for asymptotically flat black holes, and this was asymptotically ADS. So, well, of course you would have to go to the flat space version of this in order to do something analogous.
Yes. All right. Thank you, and congratulations for the talk.
Thanks.
Still, there is one question from Igor Varovic. Igor, ask your question.
Yes. Let me ask you one more question. You mentioned information problem. Can you tell your opinion about the current status of the problem?
So at the very end, you mean these things?
Yeah. I know you have papers about this. Not necessarily in the context of your 2-dimensional model.
So you're asking about the status of these 2 things, right? Or?
Yes.
Well, basically the things that I mentioned here are the things that we can compute or that we have computed. But there are still some puzzles here, especially for the supergravity case. So the construction looks very much the same. You can use all of the same words that we have been using for the bosonic gravity. We can find this heat bath and the corrections on this heat bath, but there are a couple of things that puzzle us here. So yeah, and then the charged case. Well, again, we can draw pictures for that, but so yeah, so it's work in progress. There are puzzles here and there, and yeah.
How you would formulate the information problem, like transition from pure states to mixed states, or maybe another way?
How I would formulate what? Sorry.
How you will formulate the information loss problem? In general, standard formulation is something like pure states goes to.
Yes. So well. Right. so when I discussed here about the information paradox, I wasn't necessarily saying that there is a solution of something like that I'm proposing here. I'm actually saying that there is an additional complication to it, because one usually assumes, or at least up to a couple of years ago in the firewall paradox, one assumes that effective field theory holds very close to the black hole horizon, that there are no extremely strong gravitational fields close to the horizon. So you should be able to just use quantum field theory in Rindler space, basically. No quantum gravity effects. And if you would define your operators in a diff invariant way, then there can be strong quantum gravity effects, as I've illustrated here. So it's kind of a caveat to trusting effective field theory very close to the black hole horizon. Then if you use these types of observables, then you cannot do that.
Okay.
Does that answer your question?
Yeah, thanks a lot.
Thanks.
Okay, still there is one more question from Igor Mo. Igor, do you want to ask your question? Igor Mo.
Oh no, sorry, that was a mistake. I forgot.
Okay, because you already asked the question.
Sorry,
Okay.
Nina, there was Michele Nardelli text me the question. Maybe I can ask.
Yes, please.
Oh yeah, he cannot speak, unfortunately. So no, it was just asking me if you, Thomas, can go through very quickly again slide 23 and 24.
But he already did this. But
Those are
what's the question?
The question is if you can clarify slide 23, 24. More than this, I don't know.
So I skipped these slides due to lack of time.
Yeah.
So you want me to just go through these slides then, or?
Yeah, I think that I think that was the question. Yes. From,
yes.
I see.
Okay, so maybe very quickly then. Yeah. So one can compute the energy densities contained in the Unruh heat bath, and you get the energy density, for instance, so in the quantum field theory sector by taking the coincident limit of the 2-point function. And since you already know the 2-point function and so on, you can just take the coincident limit. And that object here, well, you can write it very explicitly like that. And that is just evaluating to a Schwarzenegger derivative for any off-shell f. So again, you play the same game. You just insert this thing in the Schwarzenegger path integral. And then you get the corrected version of the local stress densities of energy densities in the bulk. So you insert this thing in the Schwarzenegger path integral and you find that TUU and TVV, so those are the two light cone components of the matter stress tensor, they're given by that expression. The first one is the one you find in textbooks, basically. This is the standard Unruh heat bath energy density. So there's left moving energy and right moving energy that is equal. So there's no macroscopic motion of energy there, and you just get the static Unruh heat bath. That's what the first term is saying. But this is a quantum gravitational correction. So there's more energy contained if you in the bath if you include the quantum gravitational correction. That's this thing. So that was this slide. And okay, so well, next to the stress tensor, you can compute the energy occupation number, and those were the plots that I have shown you. So literally omega times A dagger A, and how to get that in quantum field theory is also just Fourier transforming the 2-point function. So again, you play the same kinds of games because you know the bulk 2-point function, you insert that in the Schwarzenegger path integral, and then you do a Fourier transformation of that. And that's how you get plots like that. And now you can see, for instance, that the blue one, why it's higher in energy everywhere, because the integral of the blue one gives you the total energy in the heat bath. And that one has to be higher than the energy in the semi-classical heat bath, simply because of this formula that I showed you here, this one. So the semi-classical heat bath is this thing, but the full heat bath gets an extra positive contribution. So there's more energy there. Okay, so those were the two slides that I skipped.
Okay, thank you.
Yeah, I hope it's okay.
I don't see more question. If there is no more question, let's thank the speaker again for very instructive and very interesting talk. Thank you very much, Thomas. Thank you.
Thank you.
Thank you, Thomas.
Bye-bye.
It would be great, Thomas, if you can send by email your slides so that we will upload them on the website as well.
Yes.
Okay.
Yes.
Okay, sure.
Advance.
We'll do that.
Okay.
Okay. Thanks again for inviting me.
Bye.
Yes.
Bye.
Yes.